So another lecture over mass spectroscopy. So if we take this molecule, benzene, CH2, CH2Cl, so of course chlorine comes as two isotopes in nature. You got chlorine 35 and chlorine 37. And carbon comes predominantly as one isotope in nature, carbon 12, and hydrogen predominantly as one isotope in nature, hydrogen 1. So we won't worry about their isotopes, but chlorine, since there's a significant amount of chlorine 37, we have to worry about it because they're in about a 75 to 25 ratio. So if we added up their mass, so took the carbon's 12 isotope took its mass, there's 8 carbons, hydrogen 1 isotope took its mass, there's 9 of them, and chlorine 35 its mass. So that would have, that molecule with the chlorine 35 would have a mass of 140.039278 grams per mole. And if it had a chlorine 37 instead, so chlorine 37 has a mass that's about 2 mass units higher. So if there's a chlorine 37 in the molecule, it would have a mass of 142.036328 grams per mole. So you would see that in the mass spec, right? If you took the mass spec of this molecule, you would see a peak at 140, and then you would see 0.039278, and you would see a peak at about 142.036328 grams per mole, and they would be in about a 3-to-1 ratio. Okay, so to simplify, what we do in this class, we're going to limit the molecules to just carbon, hydrogen, oxygen, nitrogen, chlorine, or bromine. And we're going to simplify it further by just using masses of hydrogen as 1, carbon's 12, oxygen 16, nitrogen 14, chlorine either 35 or 37, depending on which isotope, and bromine either 79 or 81, depending on which isotope. So this molecule then would have a mass of 140 or 142 if we simplified it like that. Okay, so if we took this molecule and injected it onto a mass spectrometer, so it goes first into the ionization chamber, where we bombard it with high energy electrons, and if you remember from the last lecture, that knocks an electron off of the molecule, so the molecule becomes positively charged, so it's a cation, and now you have unpaired electrons, so it's a radical cation. And the point is here, is this radical cation contains a lot of extra energy because of the high energy electrons we bombarded it with. So this molecule possesses a lot of extra energy. So how can it dissipate that energy? It can dissipate that energy by basically fragmenting, by breaking bonds and breaking into smaller pieces. So there's lots of possibilities. Of course, for a molecule this small, there's not that many possibilities, but for bigger molecules, there would be a lot of possibilities. So let's just consider 3, for example. So we could either break the molecule apart, let's say here, or we could break that bond, that carbon-carbon bond, or maybe we could break that carbon-chlorine bond. So if we call this pathway A, B, and C, so maybe we break bond A, and then that would lead to these 2 fragments, for example. So benzene, this would have 5 hydrogens, but there's not a hydrogen here because that's where this carbon used to be attached at. So if you add the molar mass up there, you get 77, and that's positively charged. So the mass of this would not matter if it's not charged, because if it's not charged, it's not going to be accelerated in the mass spectrometer, so it's never going to make its way to the detector. But the molecule could have broke apart such that this becomes the radical and this becomes the cation, in which case you would have a peak for that fragment as well. But we'll just simplify it, and let's say it breaks apart like that, so that the benzene is the positive and the other species is the radical. Or if we broke bond B instead, then we could have made this fragment, and let's say that becomes the cation, and let's say this piece becomes the radical, which is not charged, so you wouldn't see it in the mass spec. You only see things that are charged because you have to have them charged to accelerate them with the electric fields. So if you add the mass of that up, it has a mass of 91. Or if we break apart bond C and we get this fragment, it has a mass of 105, and then you would have a chlorine atom. So the point is, so now this molecule that you started with, maybe that hits the detector, which ideally you want that to hit the detector because that represents the entire molecule. So you would, if that hits the detector, then you get the mass of the entire molecule. But these other fragments are in the instrument too, and they're going to be accelerated, and they're eventually going to hit the detector because you're sweeping through the electric and magnetic fields. So everything will hit the detector at some point. So what you're going to see then is you're going to see lots of peaks in the mass spec. And so these peaks would represent the molecule that is intact because it has a mass of 140 or 142, right? And then these peaks would be what are known as fragmentations. So those are just smaller pieces of the molecule. So, so the base peak is the tallest peak. So in this spectra, that would be the base peak. It's the tallest peak in the spectra, and what this simply represents is the most stable ion. So the most stable ion will live the longest, or to have the longest lifetime. So if it has the longest lifetime, then there's going to be more of those hitting the detector, so the signal is going to be bigger for it. And so this mass of 91, that's the benzylic cation. That's a very stable place to put a positive charge next to benzene ring. If you're going to have a positive on carbon, that's a good place to put it. So that's a pretty stable cation, so it lives the longest, and so there's going to be more of those hitting the detector than the other fragments, which are less stable. And then you have what are known as the molecular ion peak, or the parent ion peak. And so that would be the intact molecule that has not fragmented. So when you do a spectrum like this, so you impart so much energy to the molecule to begin with that it may totally break apart before it even hits the detector. So it's quite possible that you won't even see a parent ion peak because it may just break apart into smaller pieces. And so ideally it lives long enough to hit the detector because if you can see the parent ion peak or the molecular ion peak, then you get to know what the mass of the molar mass of your molecule is, and that's very important information. So we're going to call this the M and the M+2 peak. So the M meaning molecular ion peak, or sometimes it's called the parent ion peak, and M+2 simply means 2 mass units higher. So 2 mass units higher because of the isotope, right? So this is about 2 mass units higher than that is because chlorine-37 weighs more than chlorine-35. Okay, so so for our purposes, we're just going to mainly focus on the molecular ion peak, and we're not going to try so we will not try to interpret fragment peaks. If you're really, really good at mass spectrometry, you can interpret the fragment peaks, and that will allow you to figure out what breaks off of your molecule.